Okay, so let's start where we left in last lecture, which was a gentle introduction to operator learning, right? So this is where we focused last time, operator learning. And the idea was that if you have a PDE, you could also think of ODE, stochastic differential equations, whatever you have it. But if you have a PDE with some inputs and some outputs, you can express the PDE or this, so that you can sort of manifest the PDE in terms of what is called the solution operator. And this is going to be a mapping between two function spaces. So it takes a function input, let's say A and F from the space X, and it goes to a space Y, which is the solution. So the key here is everything is functions. So let's remember that we are dealing with functions and not with vectors. Okay, but of course, as I said, in this generality, it is very difficult to solve the problem. We have to do some approximations. And the first approximation, what we did is that we know that F here, or A and F, these are sampled from some probability distribution, mu, which is a probability measure on X, your input space. And then what we did is that we said that the dimension of this space is finite. In other words, instead of dealing with the entire problem in its full generality, we looked at what are called parameterized PDEs. So the dimension could be large, but it is at least finite. So in that case, the problem is a finite dimensional one because you have three inputs or three types of inputs. You have the temporal coordinate t, the spatial coordinate x, and the parametric coordinate y. And the important thing here is that y, this dy can be large, right? But it's finite. So I keep on repeating that. And we did some very, very basic theory, back of the envelope calculations. And what we ended up with the fact was that if everything goes well, the map is nice, the solutions to PDE are smooth and so on, still we are confronted with this challenge that the total error, this scales as 1 over square root of n. This is the best case, right? Because of the Monte Carlo rate. And this implies that we need lots of data. Lots of data in the sense that to get error of 1%, which is 10 to the power minus 2, 1 over 100, you need 10,000 samples. So this was sort of our challenge in some sense. We need lots of data. And you could say that this was primarily because of random sampling, which is a good ansatz in general. And it's sometimes unavoidable, particularly if you have in very, very high dimensions. But is it something that we could address? Is it something that we could improve? And the answer is yes, means there is, unlike in image and text, so if you think of images, you can essentially, people take images, right? They take pictures, they put those pictures into the internet, they put it into different stock image libraries, and these are more or less randomly taken. They're not designed in any particular manner. So it's reasonable to assume that those kind of images, for instance, are taken randomly. So it's a genuine answer. However, when we're doing like scientific computing, scientific problems, nothing is done randomly. We don't go and randomly solve a PDE for the fun of it. I do it, but most people don't. So then what do you do in that case? So there is much more of a design space. There's much more of a, let's say, structure to the data that we have, and we can exploit that. There are different ways of exploiting it, and without belaboring the point, I just give you one example just to illustrate that we could work with, let's say, more structured data. And this goes to a trick, as I said, this was proposed by some people here in my lab some time back. And the idea is that instead of doing random sampling, what if you have more structure in the sampling, right? So remember that this dy, it's a, if you remember in the airfoil problems that we saw, this was like dy was like 20 dimensional, right? Between 20 and 50. And in some other problems, in many, many engineering problems, this is not infinite dimensional by design because these are design parameters. You can only design so much. So you keep it within some finite dimensional space. So it's 10, 20, 50. These are the, it's not of the order of thousands, right? So in that case, what you can do is that you can use a different type of training data, or you can generate different kinds of training data. And this is sometimes a useful trick. So instead of doing random sampling, so remember that our alternative was random sampling. This is in blue. What I do here is sampling using what are called low discrepancy sequences. Now, I don't have the time to give you all the details, but the idea is very, very simple. And let me try to explain it through this picture here. So this is just in the unit square in 2 dimensions, 0, 1 squared. And let's look at how random points. So random points underlie the Monte Carlo method, right? So these are random points. They underlie the Monte Carlo method, for instance. And as you can see, so I divide this square into smaller squares. I have 25 of them. And the idea is that if you take random points, you cannot guarantee that these points land in the right squares. Means in every square there is a point. In fact, you can see that this square there is no point. This square there's barely a random point. This square there is no random point. This square, and so on. So on the other hand, there are some squares. For instance, this one there are almost 6 in the vicinity. 5 or 6 in the vicinity. That's the whole point of randomness, right? Because there is no structure to it. You just take random, and then in the next draw, you could get something else. In the next draw, you could get something else. And if you have lots and lots of draws, of course, you fill up the whole square. That's the whole point of randomness. However, we cannot have that kind of, let's say, we cannot have so many random draws. We can have at best 1 or 2. So then you don't fill up the whole square. So what if I designed something, of course, which is going to fill up the whole square, while at the same time being better distributed in some sense, right? Of course, your answer would be then just take the center of each square. That would solve the problem, right? All the squares will be covered. But then you can see that per dimension, I will have 1 entry in each square. It's essentially like the number of grid points that I will have. And that, of course, blows up a dimension. So just imagine that if I have 10 dimensions, and in each dimension, I have 5 points. So I have 5 to the power 10. And that's too much, right? Random, of course, if I draw 1,000 points, it doesn't matter. They get sprinkled all over. So there is a compromise between uniform grid points, which is what you do in 2 or 3 space dimensions. 3 is almost the limit of that. And random points, which is, okay, if you have a million dimensions, and if you have infinite dimensions, as you will see, there is no choice. But in finite, but large dimensions, let's say 10, 20, you could do something else. And these are precisely what are called low discrepancy sequences. There is, earlier I used to teach much more about it, but there is probably no time to do that. So the idea is that they're simply better spread out. Okay, so I'll give one example of this. It's called Sobol sequence. It's a very popular one. And these are the orange dots, and you've got orange stars rather. And you can see that they are much, much better spread. For instance, this place where there is no random point, there is a Sobol point. Here, for instance, where was this one? There's a Sobol point. This one, there is a Sobol point. This one doesn't have a random point. It has a Sobol point. Of course, sometimes they're not. Like this one has no Sobol point, even though they have 3 different random points. So it's also not perfect, but it's relatively better than random points because these sequences are what are called equidistributed. So there is a precise mathematical definition that I don't have the time to give, but essentially these are equidistributed. Roughly speaking, they are better spread out, even though they don't incur the curse of dimensionality, or they have a mild curse of dimensionality, as you will see in the next slide. And there are a dime a dozen of them. There are at least 20 or 30 different types. They're very, very easy, just like you use. So these are behind what are called quasi-Monte Carlo. So just like random points are behind Monte Carlo, these points are behind what is called quasi-Monte Carlo. So if you go to, I don't know, SciPy or any standard library, and you search for these, there are many, many different ones. So I just showed you 2, Sobol and Halton sequences, the one in orange and one in green. You don't have to learn so much about them, just like you use a random number generator to get random points. You can use a quasi-random number generator to get these kind of points. And this is a fairly easy piece of code. And what is the advantage of them? The advantage of them is precisely given in the next slide. Okay, so as long as your map that you're approximating, so remember that this map here, this could be the field. This could be the field u of txy. Now z is the entire thing, txy, or it could be an observable. So this is what I called as L of y, right? In this case, z would be y. So this could be a field or observable. Field would be the whole flow field around the airfoil. Observable would be the lift and the drag. Then as long as this function has certain structure, so first of all, it has to have what is called a bounded Hardy-Krause variation. So this is not that difficult. It's just integral. So your underlying map, let me call it as L. So dy of L, let's say, this is dy1, dy2. These are mixed derivatives. Okay, this dy, this guy is going to be finite over dy. This is going to be finite. So it's not derivatives, but it's just mixed derivatives. As long as this mixed derivatives are finite, so this is morally the Hardy-Krause variation. The function has to have some structure. The map that you're going to approximate has to have some structure. It can't be discontinuous, for instance. Then you can prove very easily that your total error, remember that this is a familiar quantity for us, the total error has two parts, training error, optimization error. This we cannot, but now this is supervised learning, right? So it does not have all the problems that pins have, because you don't have this square Hermitian of the differential operator or anything. So this is standard supervised learning. And then you have this Hardy-Krause variation that comes in. So if it has large Hardy-Krause variation, then of course the constant blows up. But you need a smooth activation function. ReLU, for instance, won't work because it doesn't have mixed derivatives. But hyperbolic tangent or smoothened versions of ReLU, GELU, GIGLU, and so on, they will work. And then the key point here is that you get 1 over n. Okay, there is a logarithmic correction. As you can see that there is a logarithmic correction. So if you remember, if you have for random sampling, and this is where the number random sampling was the errors, if the training error was small, was 1 over square root of n. And here, let's say it's with this low discrepancy sequence, LDS, low discrepancy sequence sampling, then the error is going to behave like 1 over n. Okay, so of course, this required for 1% error, 1% error, this required 10,000 points because 1% is 1 over 100. This, on the other hand, requires 100 points. So it may not seem much 1 over square root of n, 1 over n, but when you do the math, you really get a lot of benefit. You know, so if each sample takes about 10 minutes or 2 minutes to generate, like we did for the airfoil, a factor of 100 is quite a bit of saving, right? So, and in 3D, it's even much more serious. So this is an example where this problem with large data, the fact that you need lots of data, as long as you're in this parametric setting, and if you have reasonable number of parameters, then it's okay. But of course, eventually, this is a good part, right? The 1 over n, this term is good. But that just like there's a denominator, there's also a numerator. And this numerator is this logarithmic term here. And this is the bad one, because this depends on the underlying dimension. Actually, this should have been d of y, but I'll correct it in the slides. Right? So, of course, if n is 1,000, log n is just 3, means there's nothing. But 3 to the power something, right? Once the dimension starts kicking in, this becomes a serious thing. So let's say that there is a cutoff for this, and the cutoff is roughly 50 dimensions, because beyond 50 dimensions, you don't have a choice, okay? So at least for some of these problems, this is going to be very, very useful. And I'll show you an example. But so far, is this clear how this sort of by better spreading out the sampling points? And we can do that because we are not taking images, we are not trawling data from the internet, text data from the internet, but we have the capacity or the power to generate data, because we can always generate data through numerical simulations. We can do it in a much more targeted manner. So this is roughly the moral of the story here. And once you have that, then of course you can go and try to solve the problem. So if you remember what I started out with, so this was this problem with flow past an airfoil. So here is the airfoil. This is parameterized with, I think, 20 parameters. So dy is equal to 20. And then what we are looking here is, so this is what we are predicting is the whole flow field. So we can also predict the lift and the drag. These are the important observables, as you will see later on. And then we have a very, very small, this was done some years ago. So there is, you'll see towards the later half of the lectures that we'll end up with DNNs, which are hundreds of millions of parameters, right? But for these kind of simple problems, you don't need such big networks, simply not enough data to train them, right? So here you just have something like 10,000 parameters. Perhaps I don't remember the exact configuration now. It was maybe 10 layers with or 5 layers with 100 parameters in each layer, something like that. Nothing big. And you have very few training samples, 128. This is reasonable. You could afford to have 128 training samples. And to generate these samples, this was done with a very, very high accuracy, because as you can see, the shock here is very, very sharply resolved. All these regions are very, very sharply resolved. So there is a grid that is very fine. And then, of course, it takes time. It takes about 40 minutes on a laptop. This could be speeded up if you do things in parallel, but let me give you the raw numbers here. So it takes about 40 minutes. If you don't want a very fine resolution, you can get about in 1 to 2 minutes. Okay, this is sort of, but this is a very fine resolution. This is the ground truth. And then you can see that for the lift and the drag, we could get very, very good results, 1 to 2%. Even for the whole flow field, we could get to 1 to 2% results, right? The training, you generate the 128 samples. This is some additional cost, means we don't count that. But once you start training at that time, it's faster now because the machines are much faster. It took approximately an hour, okay? Whether you took the lift or the drag or the whole field, it took approximately an hour. And the point is that you got very, very low errors, which is good. This also looks quite okay. Not exact, as you can see, that this region is not completely well resolved, but of course, this is an approximation. This is where the 1% error comes from. But the most impressive number is what you see here, right? So remember that the underlying simulation took me 40 minutes. If I wanted to predict the lift and the drag, which are the real quantities of interest here, it would take me 40 minutes because I have to compute the flow field. Then I have to compute some integrals. These integrals will take me, I don't know, 10 seconds to compute. That's not the problem. It's the flow field that takes a lot of time, right? So you compute the flow field and then you do the evaluation, and this takes you 40 minutes. But once you have the trained neural network, it takes you no time because this was like not even 10 microseconds, right? To 10 to the power minus 5 seconds. For the whole field, it took a little bit longer, but it's still of the order of 1 over 100, 1 over 10 seconds. It's sort of the whole field means you have to fill in every single point. Drag and lift, you just have to give one number. So this shows you that in principle, if you're able to train, so these kind of neural networks or models, these are called what are called surrogates. Let me write it. I don't think I even wrote it down anywhere. So these kind of models are called surrogates because they are surrogates for the entire physics here, the dynamics here, right? And the advantage of this is that you get very, very fast, quick evaluations. Of course, but this was done, the reason why it worked in some sense was this was done with LDS, with Sobol points, Sobol sampling points. This was a point that I wanted to illustrate, right? If I did random training, then of course the errors were larger because remember that the errors decay with 1 over square root of n. In particular, the drag was useless, right? If you have 23% drag, you can't do anything. Lift was okay. Lift is somehow easier. It's more linear in some sense. Drag is much more non-linear. You'll see in some sort of the whole distribution of lift and drag in a minute. So this tells us that the method works provided that you're able to confront with this data challenge, right? So if you needed, if you wanted 1% for the drag, then you probably had to take 10,000 samples or 100,000 samples. If you remember that this error decays very, very slowly, whereas the error here with the Sobol points, it was decaying linearly at least. And there are some problems for which you can do quadratic or even hyperquadratic and so on, but this is beyond the scope of my lectures today. Yes, absolutely.
What would be the difference between the drag, 1.87 and 23.4? Is it a different, like, one uses Sobol sampling?
Yeah, that is the point. Yeah. Monte Carlo. Yes. So there is a huge difference because, and the difference arises from the fact that there is theory behind it. So you understand also why this difference arises. This difference is precisely due to this factor here. Okay, good. Thanks for the question. And now, so the bottom line is it works, provided that you have this data challenge, you have parameterized everything properly, you have good training data, and so on and so forth. Now, once you have this surrogate, what can you do with it, right? You just don't stop here that you make a prediction, you do something beyond, some downstream tasks, okay? And the first downstream task that you can think of, so let me even write it down. These are called downstream. So prediction is just one part of the problem. In engineering in particular, you don't just predict something, you know, you want to do something with it. You want to design, you want to optimize, you want to control, you know, that there are some end results, some end goals that you want to evaluate. And this is done, these are what are called downstream tasks. And here is a very simple downstream task. It's called uncertainty quantification, okay? Uncertainty quantification, roughly speaking, this is a topic by itself, it's a huge topic by itself with lots and lots of books that are written on it. But the way I think of uncertainty quantification, to explain it in one slide, is that you want not just one particular value, but you want the whole distribution. Okay, you want error bars. So if you think of it, all of you might have done experiments, gone to the lab and so on, and then you need error bars because every experiment has certain uncertainty and there are some error bars. So what are the error bars in this particular point, right? So for instance, in this example, so this is just a flow past an airfoil, similar example to the one that I have. Now, you know, when you manufacture, there could be some small impurities in the shape, right? Because the shape is never perfect, it's never perfectly manufactured. But at the moment, we are not even considering that. But the point is that here the uncertainty comes in from the fact that you have some flow, right? So there is some incoming flow. So you make some assumptions on the incoming flow, and these assumptions are based on what is the incoming pressure, what's the incoming Mach number, what is the angle of attack. The angle of attack is where the flow hits the airfoil. It's typically 1 degrees, but it's of course not exactly 1 degree. It could be 1.1 degrees, it could be 0.9 degrees. Similarly, the incoming Mach number, I don't remember now, it's probably 0.8, but of course, who says it's 0.8? It could be 0.78, 0.82, and so on. So there is a distribution. So in other words, inputs to the PDE, inputs have some, let's say that there is some uncertainty in the inputs. In this particular case, these are parameters, also could be in the shapes, right? So because these yi's, they belong to some space y, and there is a measure on y. Let me call it as nu, because it's not a measure on the function space. It's a measure, this is a probability measure on y. And you generate the samples. So the uncertainty comes in from the fact that you cannot be precise with your inputs. Your inputs have some uncertainty in them. Okay. Now, once you have this uncertainty in your inputs, of course, you have an operator. So you have some uncertainty in the output, right? So in other words, this uncertainty in the input is what is called, so what is UQ or forward UQ, because there is also inverse or Bayesian UQ, as some people call it. So UQ is essentially, roughly speaking, very roughly speaking, will be the statistics of the measure. So you have your operator L, and this is what is a push forward, okay? In other words, if you have some input uncertainty, how does the solution operator translate or propagate? It's also sometimes called uncertainty propagation. How is this uncertainty propagated by the solution operator, right? So here is a typical example. So you have these uncertainties in the flow conditions, and then as you can see, well, we have to quantify that uncertainty. The histogram of the lift, for instance, this is in blue here. So the histogram tells you that the lift is distributed, there is a distribution. So sometimes you can have very high lift, 1.2 even. Sometimes you can have very low lift, 0.8. But it's mostly like a truncated Gaussian with the values around 0.8. Okay, so that's good. So that's where the lift is. So, but there is a distribution to the lift, and this distribution comes in because of the uncertainties in the flow. Okay, so in every physical system that you have, there are some intrinsic uncertainties. And these uncertainties, they can be modeled. You can model the input uncertainties. So here we model the input uncertainties with the prior, which is a uniform distribution. Well, what else, right? But if you look at the drag, for instance, even though the uncertainty in the inputs, these were the flow parameters, as I told you, angle of attack, Mach number, and so on. So in the lift, you get some sort of a Gaussian behavior. In the drag, you get a very, very non-Gaussian behavior. And this is because it's a nonlinear problem, right? So the inputs are getting translated or transformed into something which is highly nonlinear. So there is that element here, and you can see that this is much more of a what some people call a beta distribution, probably, or it's sort of a very, very peak distribution. Most of the drag is around 0.006, but there are some extremities when the drag can be 0.1, means then that object essentially cannot fly. If the drag is 0.1 and the lift is 0.4, the lift to drag ratio is 4, no object will fly. You need a lift to drag ratio of approximately 100 or something to fly. But this can happen, right? If there are some extreme flow conditions, then you cannot do anything about that, right? So the idea is to propagate this uncertainty. And how is it done in engineering? This is the same with the weather. So when you go to Meteorschwitz, you open your app and you look at the uncertainty of weather. How do they calculate it? So they have some inputs to the weather, right? So these are the temperature at this time, the pressure, the precipitation, all kinds of different parameters. And they know that there is some uncertainty in them, because when they do the data assimilation, there is some uncertainty. They run the weather forecast. I don't know how many ensembles they run now, but some years ago it was 50 ensembles. So they would run 50 ensembles. Weather forecast is very expensive to run. It occupies quite a bit of time at CSCS, at the big supercomputing center here. And then what happens is that you take 50 members of the ensemble or 100 members of the ensemble, and then you compute the statistics and you get some uncertainty. Okay, it's a little smarter than that, but morally speaking, that is what is going to happen here. But now 100 is nothing. Remember, this is the Monte Carlo sampling at the end of the day, and 100 samples, the error is 1 over square root of 100, as a square root of 100 is 10%. So it's not, you can have large errors. So you need lots and lots of samples, again, in order to be able to compute this uncertainty. Sorry, let me get some. So now if you need 1,000 samples or 10,000 samples, how do you do it? As I said, the weather forecast was run many, many times, right? Now running the weather forecast is expensive. So you cannot do it 100 or 1,000 times. It's the same here. Remember that for a high resolution simulation, it took me 40 minutes. But for a low resolution simulation, it would take me 2 minutes. And if I do 1,000 of these or 10,000 of these, again, I'm not in business, right? Because it takes forever. So what we're going to do now, and this is a very simple algorithm, is once you have, so this L star here, so remember that Monte Carlo sampling, you could also do it with quasi-Monte Carlo, random points, quasi-random points, right? Like Sobol and Halton and so on. But essentially what you could do is that you just, this is the Monte Carlo. So you take, this is written in some mathematical notation, but essentially what is going on is that you take M samples of the input, you propagate, you run your code M times, and you average them. So that is going to be you average and you compute the statistics, right? But instead of using this, you take some samples, you train your neural network, okay? Because now with 100 samples, you can train your neural network quite well. We have realized that. And then remember that then I can take this M could be 100,000. I don't care, because for instance, for the lift and the drag, it was 10 microseconds, right? So even if I take 100,000 samples, I still am in 1 second, because that's the training is taking its time. There's no choice about that. It takes you some time to generate the samples. It takes you some time to train them. But once you do the inference, it's very, very fast. So it's the same here. Means if you would have done a direct forecast, you would have taken 10,000 samples, which would take you X amount of time to train, X amount of time to run. Now I say I run 100, right? It takes time, 40 minutes, let's say, or let's say 10 minutes for each sample. You can parallelize it. That's not a problem because these are sample independent. But nevertheless, it takes time. But once it is there, it takes 1 hour to train. And then to infer, it takes me no time whatsoever. Right? So this is sort of the algorithm. It's more or less online. And then if you look at the speed up, first of all, the results are very good because, of course, your surrogate has been trained very accurately. So there is little scope for errors. And you can't really distinguish between the probability density functions, the PDFs, the histograms in this particular case that you get from your surrogates and from your ground truth, in this particular case with the Monte Carlo, the quasi-Monte Carlo run. So in fact, if you just looked at the uncertainty using Monte Carlo, not training with Monte Carlo, just the original uncertainty quantification using Monte Carlo, you get two orders of magnitude, sometimes even 3 orders of magnitude. But in this particular problem, you get 2 orders of magnitude speed up. And this includes the sample generation time, because otherwise I could have just used those samples to do my uncertainty quantification, right? So in one case, I generate all my samples, and then I do my uncertainty quantification. In the second case, I generate a few samples, do my training, and then do my inference and uncertainty quantification. So what is the speed up that I get? If I would have used Monte Carlo as my base algorithm for uncertainty quantification, these are very, very impressive numbers. But of course, we know that Monte Carlo is not optimal. The real test is what if I would have used quasi-Monte Carlo as my algorithm here for my base algorithm. Even with that, there is a speed up of 1 order of magnitude. So there is a speed up. It's more modest because you're using a state-of-the-art let's say algorithm for uncertainty quantification, but even then a factor of 10 is nothing to laugh at. And this is for this particular problem in 2D. In 3D, these speed ups are much, much more. So the point is, as soon as you can do this surrogate training, there's something cool that you can do with it, right? There's something good downstream that you can do with it. And I think one of your exercises, if I don't remember, has this element in it. Okay, are there any questions here? No? So everybody understood? This was a very, very quick introduction to uncertainty quantification because, yeah, we have more interesting things to do in some sense. Okay, so let me show you another downstream task, which is even more vital. And this is what is roughly called as PDE constraint optimization. Okay. So what is PDE constraint optimization? So this is design essentially. And let me, instead of giving you a very general picture of the whole thing, let me give you a concrete example because it's very easy to communicate, convey what's going on with this very simple example. And this would be the problem that we started with, which is the shape optimization of airfoils. And the idea is always that you're going to do this optimization in order to increase or improve the aerodynamic properties, right? Because this is an more optimal airfoil is someone which has better aerodynamic properties. Okay, so what do you do in this particular case? So remember, the way we set the problem up was, so we have some reference airfoil. This is how people do this in Boeing or Airbus or any Dassault or any company. This is the process. It's just a toy version of it. Okay, so you start off with some reference shape, which is given in black here. This is some standard shape that people have, let's say, realized through intuition, because you don't start with a square and then try to optimize it to an airfoil. We know that a square or a circle, a plate is not going to fly. So you have to start with something which is aerodynamically reasonable, right? And then you start with this, and this is my reference shape. And then roughly speaking, I'm going to perturb this shape. I have this design envelope. I'm going to perturb this shape by using what are called some Higgs-Henne basis functions, okay? These are some splines. You can think of them as some sort of splines. These are usually, as I said, means my D is, or D bar actually in this particular case, is anywhere between 20 and 50. Because I also need to manufacture them. It's important to manufacture this, right? I don't need to give you the details, but what I can tell you is that all the shapes will have to lie within this design envelope, because that's what this spans, right? You can't have arbitrary shapes. You don't want to parameterize this airfoil into a circle. You only want to sort of parameterize it into reasonable aerodynamic shapes. And these have been designed with a lot of intuition because people have been designing aircraft. The first aircraft that the Wright brothers designed didn't have any of this. They just went and they flew something. But these are bicycle mechanics trying to sort of fly an airplane. They didn't need to design it like that. But today, modern design, you have this intuition that has been built in for 100 years, and then you go through this process, right? And then what you need to do is to find these parameters, this yi's, such that I have some airfoil shape. For instance, the typical objective function is to you fix lift because you want the plane to fly. So you fix lift around the reference airfoil's lift. So the reference airfoil has been designed to fix lift, but then you minimize drag. In other words, you take the lift, it's a constant, and if you divide by the drag, this lift to drag ratio, it increases, right? So this would be another design objective. So mathematically, the objective is very simple. You have an objective function. The objective function has several elements. The first element, of course, is why do I have a pink? My children, they play with this all the time. So this is essentially the drag coefficient, CD. For each shape, we have the flow conditions that are fixed. These are the cruise conditions that I just told you. We want to minimize the drag, right? But we want to keep the lift constant. So this is the lift coefficient. Okay, this is the lift coefficient, and this is the reference lift. We want to keep it constant. So we have some penalty parameter, which is, let's say, 1000. 1000 means that I really penalize strong deviations from the lift. And similarly, these are what are called structural conditions, structure. What do I mean by that? At the end of the day, I need to manufacture my airfoil. So what happens is that just imagine that the shape that you're designing should have some structural stability. And the way in which aerospace engineers measure this structural stability is that they would like to fit a beam with certain structural properties inside the airfoil so that it can't compress too much. Okay, so these are some structural conditions. They can be there are, so let's say there are constraints on the area of the airfoil. It can't become too tapering. It can't become too light in some sense. Okay, so these structural conditions, they are also expressed in terms of penalization. You want to retain some structural stability, you want to retain lift, and within those constraints, you want to minimize drag. So this is done using a constraint optimization algorithm or penalization algorithm. These are not exact constraints, but they should be kept relatively constant. And then you want to minimize this. Now, all of you have learned, Ben taught you in the very first lecture, that when you have, this is by no means a convex function, okay, because there are these inputs, they go into this lift and drag are not quadratic by any means, right? So this is a non-convex optimization problem. And then what you need to do is to sort of minimize it, right? So you could use gradient-free optimization. Some people use gradient-free optimization, but the standard one is to use gradient-based optimization or gradient descent. And you know what gradient descent is. So gradient descent, how many times have we written it? This would be yk plus 1 equals to yk minus some learning rate gradient with respect to y of j of yk, right? So you need gradients. So you take the gradients and you move in the direction of the negative gradient, and eventually it will converge at least to a local minimum. Now the problem is, how do I compute my gradients? Okay, so now this is the hard part. How do you compute the gradients? You cannot take finite differences anymore because you don't have this grid structure. Even if you did, because this is a high dimensional space. Remember that the y is at least 20 dimensional. So you cannot take finite differences in order to compute the gradients. So what people do is they use what are called adjoint solvers. So this is a direct problem. There's an adjoint problem. You write a PDE for the gradient. This can be done. It's a very complicated PDE. It can be done. And then at each step, you have to solve the PDE itself and then use that to solve the adjoint PDE, compute a gradient, move, solve the new PDE, compute the gradient, and so on and so forth. So the solving the PDE, remember that it was anything between 2 minutes to 40 minutes. Adjoint is even more because adjoint is a harder nut to crack. Okay. So per step, it could be anything like 1 hour in 2D. In 3D, you can imagine the cost accordingly, and you have to do it over thousands of steps. So this is a very expensive process. And big aerospace companies, they spend a lot of their compute on this. Almost all their compute is spent on these kind of problems, right? So that's why I said that it is either it's very expensive or it can even be infeasible. We'll take a little longer maybe before the break. It can be even infeasible, particularly when we are doing optimization under uncertainty. So here I said that everything is fixed, my cruise conditions are fixed, the Mach number is fixed, the angle of attack is fixed, and so on. But before that, I told you that these quantities, these are uncertain, right? So there is some uncertainty there, and you want to optimize under that uncertainty. So that will give you additional overheads. So this is a hard problem in some sense. And this is the same if you have cars, if you have whatever in shapes, any kind of engineering design, this is precisely the problem that is there. So now, of course, the simplest thing that you can do is now we know the trick, right? We take some shapes, we have the data, we generate the data from the simulation, we train the surrogate, which is the deep neural network, and then simply use the gradients of the deep neural network. That neural network, all the gradients can be computed with backprop automatic differentiation. So this is very easy, right? So this is somehow, as I said, so you just take a training set. This could be random points or Sobol points, as we know is better. And then you take neural networks. These are going to output the lift and the drag. And then you just use this as your objective function. Instead of using the area is anyway independent. It's a structural constraint. So instead of using the CFD simulation, which is expensive, what you do is that you just use the deep learning surrogate because you have a very accurate surrogate, right? So in that case, evaluating the gradient is trivial. We have small networks, we do backprop. So how much time can it take? You can even evaluate Hessians if you want, if you use LBFGS or approximate Hessians. And then you just run this optimization algorithm. So all your cost is in the training process. Once you have done the training, once you have done the data generation and your training, then of course the inference is lightning fast, right? So it doesn't take any time. It's very, very cheap. However, there is a little caveat there. And the caveat is very, very well expressed by this picture here, which tells you that now when we train, we take random points or Sobol points. These are spread over the entire space, right? There is no There's no structure to these points. Though, in fact, Sobol points have even been tailor-made to be distributed over the entire space, right? That over the entire design space. However, optima do not lie at random places. Typically, optima lie on some manifolds, on some curves in the space. And because of that, so essentially, roughly speaking, if you want to draw a picture, which is what I should have done instead of giving you this picture, but I prepared it on the train yesterday. So essentially, your training points are all over the space, right? Something like this. So these are your training points. On the other hand, your optimizers, these typically lie along some curves like this. So this is your optimizers. So when you take random training points, the risk is that you are not approximating the optimizers well, right? And because of that, of course, if you take enough training points, no problem, because then it will fill up the whole space. But if you don't, then you don't approximate the optimizers well. And this has been shown here in this plot here, that this is the lift to drag ratio. And if you take 2048 points, then you spread, and then you see that, and you are targeting this region here, right? Because you want high lift to drag ratio. So you want to have as high a lift to drag ratio as possible. But if you take 64 points, bulk of them, because the way things are distributed, they will lie in this area here. And so you're, so just imagine that if you would have optimized, most likely you would have gotten a lift to drag ratio of 100, which would be half as effective as the real lift to drag ratio, which is out there. So you're not able to sort of explore the entire design space in some sense. Of course, if you're lucky, there is also 120, but it's still, you're significantly underestimating the minima and the optima in this particular case. And this is the reason why it is happening, because you're not filling the optimizers well. So in this paper, I can send you I can put a link. We have an algorithm that somehow iteratively constructs this optima. So instead of taking these points randomly, it starts with a random version of these points, trains the neural networks, provides some approximate optima, takes these as your random, as your new training points, keeps on iterating so that it better fills up the space. But again, I'm out of time, not space, but time. So I'm not going to do that. But the point is, it's essentially based on having better training, adaptive, what called active learning algorithms for this particular problem. And does that work? The answer is yes, at least in this particular case. There are some other examples in the paper, but this one is very interesting. So as I said, my reference drag was essentially 115 units, as this is called. And after optimization, it was 58 units. So you reduce the drag by a factor of almost 2. That's why the lift to drag ratio went by a factor of 200, right? Means the lift remained where it was. So it was 87 units and it remained at 88 units. So almost 50% of the drag was reduced. And here is the reference shape. And the absolute minimum, as you can see, this is a very, very tiny perturbation, right? The shape itself is a tiny, tiny change. And in this particular case, this is a very idealized case. You know, in real airfoils wings, you cannot get 50% drag reduction. You get 5%. But 5% is $5 billion of less fuel. Because that's, at the end of the day, these things have to fly. You have to pay for the aviation fuel, which is very expensive. So this is, in this idealized case, no human could design this tiny, tiny perturbations, right? So this is impossible. This is why we do automated design. And in fact, if you look at the comparison, okay, that's nice, but what if the same, these are impressive in some sense as raw numbers, but what is much more impressive is if you take so this iterative algorithm, not the base algorithm that I told you with deep neural networks. So this is the traditional algorithm. It has a name TNC based on the optimizer. But to get the same results, you are in this region here. So this region is 2048 forward solves. Okay. And in comparison, you get something here, right? So this is like 80. So 80 forward solves, because you need to train this network and you used 80 simulations to do that. That's the way I measure. And remember that this is doubled. So it's really 80 and 4,000. So a factor of 50. You gain a factor of 50. This was, of course, proof of concept. As I said, means in this particular case, there are many idealizations. But with this algorithm, it really worked. We have some version of it in 3D, but that's more of a detail, right? But the essential point is a well-trained neural network can be the basis for many, many downstream tasks. And just I'll end by showing you how the flow looks like so that you have some idea. So this is how the flow looked like on a reference airfoil, right? So there, most of the drag is caused by this shock here. Yeah, that's the whole point, right? But if you look at the best configuration, all that it did was this, you can't, there's no visible difference between the shape here and the shape here. They're slightly different from each other, right? But it did change the characteristics of the flow quite heavily, because there was some tiny, the shock drag reduced, and as a consequence of it, there was a 50% reduction. The point is, first of all, this cannot be done by humans in some sense. Second, it's expensive to do it by traditional numerical solvers. And once you have well-trained neural networks, they can do it rather well. So you can do these kind of downstream tasks very well. And I put this up front because now I'll not talk so much about downstream tasks. I'll focus almost entirely on prediction. Because once you have prediction, maybe if I have time, I'll do something on inverse problems, because that's very different types of downstream tasks. But what I'll do is I'll focus on prediction. So from now onwards, we'll not talk about uncertainty quantification, not talk about shape optimization, control, but you know that all these can be done if you have a very good predictor. Okay, so with this, we are going to stop. We reassemble at quarter past, okay? Quarter past, so that we can have a second part. Just pause the recording. Okay, so let's restart. So it's somehow the narrative of the course is that we start with something, say that it's the best thing, and then demolish it, and then start with something else, say that it's the best thing, and then demolish it, and keep on doing it, and keep on doing it. But that's how science is, you know, particularly for a new field. You think that, oh, this is the best thing, but then you realize, this is under the investigation, that's not the case. So I explained to you so much about parametric PDEs in the last 1.5 lectures. But now I say what are the difficulties with it, and this will be the recurring theme. That is, you'll find out that this is things are in such a state of flux that there's no ultimate solution yet, which is good, right? Because then there are things to do. Okay, so what's the challenge with parameterization? So everything was good now, right? So I cheated. I had an infinite dimension problem, and I simply said, oh, we can approximate everything in finite dimensions. But well, the difficulties of parameterization. So the first one, which is a very practical one, is that it's difficult to come up with it's very difficult to come up with one, right? So remember that these parameterizations that resulted in these shapes, these have been done with many tens of 10, 20, 30 years of engineering experience. That's why we were able to come up with parameterizations like that. Now, if you're going to design a little vehicle, a drone of your own, means there is no such parameterization that you can use, right? So you have to handcraft it. This is problematic. But there are even more difficult issues with it. Of course, needless to say, it's not unique. So here is, and because of that, there are some issues with generalization. So what does it mean that it is not unique? So here is a parameterization, which is exactly two different parameterizations give you the same answer. And it's sort of very easy to see that. So I can have a function, parameterized function, parameterized by single parameter x, which essentially realizes function x squared, the quadratic function, right? But if I didn't know that this was the case, I could also come up with the following parameterization. Y1 is some a1 of x plus b1. Y2 is a2 of x plus b2. And I can take any of these a1, a2, b1, b2. I can come up with y1, y2. And I can rewrite my function instead of a function from one parameter to vector to an output, a scalar output. I can write it from two parameters to a scalar output. And I will, here I have taken half and half, but I could take 1/8 and 7/8, or 1/4 and 3/4 and whatnot. So the bottom line is, the bottom line rather, not the bottom line, is that there is no unique way in which you can do the parameterization. So now, suppose I wanted to learn this function, and I wanted to sort of I learned this function. I take data from one space dimension, I train it, and of course I can realize the quadratic function. But then someone says, okay, apply your method to learn the function from in these parameters. And then you fail completely, because your method takes one input and produces one output. Without realizing that it's exactly the same function that can be realized by taking two inputs and producing one output, or three inputs and producing one output, or 100 inputs and producing one output, right? So this is the issue with parameterizations, that these are not unique. And because of that, they don't generalize well. And this is sort of the key in machine learning, because machine learning is all about generalization. And if you don't generalize, you have not properly machine learned something. So what does it mean in this particular context? And why do I highlight this so much? So from now onwards, I will keep on sort of harping on this word generalization quite a lot. Okay, so here is an example, which is quite instructive in some sense. So this is the same Higgs-Henne airfoils, the way that I told you. And here I took an input dimension of d equal to 20. So this is how the airfoil looked like. And this is very much in the setting that we had, right? So this particular set, where is it? This setting, 20 dimensions. So you could generalize the airfoil. But now someone would say that, okay, 20 dimensions, you have trained your neural network to produce something in 20 dimensions. And this is the ground truth, but the neural network can do a very good job in approximating it. That's what we said, right? But now, for some reason, someone came up with the idea that, okay, actually, there's a more optimal version of this airfoil, which will be here. It's more sort of tapering, instead of being so flat. It may not be the case, but it's just to tell the story here. So this, on the other hand, I cannot parameterize with 20 dimensions anymore. I need 30 dimensions. Because the spline functions, 20 spline functions are not enough to parameterize it. I need 30 dimensions. So this is how this airfoil looks like. So what can you do? Can your neural, and the flows, they are, of course, there is a slight difference, but they're not completely different from each other. Maybe as you can see, this is, the flow is more or less of the same type, right? So in principle, generalization would have meant that my neural network, which has learned on this shape of airfoils, I can apply it either zero shot to the new configuration or fine tune it, as some people call it. Use a little bit of data and fine tune it. But I am finished, right? Because remember, what did my neural network do? It took 20 inputs. Of course, it also took the spatial coordinates as inputs, but that's the same. Let's say it took 20 inputs and produced me the lift and the drag. Now, suddenly you are giving me 30 inputs. What do I do? I don't have any training data to go from 20 to 30, even though the airfoils themselves are very, very close to each other, right? So in principle, I should be able to learn one from the other. But because I use this particular strong parameterization or strong reduction of my compression of my information, I'm left with no choice. Because, okay, now how do I go from 20 to 30? I don't know. I certainly cannot do it zero shot. I need some mechanism by which I can go from 20 to 30. But then someone will say, okay, the mechanism is very simple. You should have started out with 30 parameters. And instead of taking the 20 parameters, 20 active and 10 passive parameters, that would have done your job. But then someone else will come, okay, let's have something with 40 parameters. Maybe it's even more. And what do? So essentially, parameterizations are necessarily limiting because the input, remember, at the end of the day, you had to work with a function space input. Because if I had to deal with functions and just think of these shapes as functions, level sets, so these are level sets of some functions, then this guy here and this guy here, they're close to each other. There's not a huge difference between them. But if I think in terms of parameters, they're far from each other. Means they're not even in the same, they cannot even be compared. Something is 20-dimensional, something is 30-dimensional. And another way to do it, to think of it, is just imagine that if you had a function, just think of it. It's a very intuitive way. So let's say I have a function f. Okay, I can rewrite this function as some Fourier series. Let's say sine kx, Fourier series. Expand the function, right? And I take another function g. I expand it gl sine lx. And let us say that my fk is equal to gk for 1 less than k less than 20. They have the same coefficients, okay? So, but in one case, I have my k from 1 to 20. And in another case, I have my L from 1 to 30. And let's say that GL decays like 1 over or exponential to the minus L between L and 20 and 30. They are going to be very, very close to each other in some sense. So these two things are very, very close to each other. But suppose I would have used my FKs as my parameters and GLs as my parameters. For the first 20 parameters, they're exactly the same. I would have done whatever, right? But as soon as I go for the whole function, even though as functions, they're very, very close, as parameters, they're not comparable at all, right? Because one has 20 and the other has 30. So you see, so this is necessarily limiting. It's just a concrete example of this problem, that this is not a natural way. Of course, it's a pragmatic way. It's a practical way that you write everything in terms of parameters, but it's not a natural way because there is no sort of connectivity between the two. One is sort of disconnected from the other. So unfortunately, even though these are sort of good baselines, they can be useful in certain contexts. But in general, you have to stick back to operator learning. You have to work with functions. You have to, but we learned some tricks, right? We learned that we could use some representations, we could do some downstream tasks and so on. So it's not completely useless. But nevertheless, we have to deal with the beast as it is. We cannot just chop it off into pieces. And the beast is that you have to learn the inputs and outputs are functions. So here is a function, and here is another function. And in the next few lectures, we are going to deal with that, right? And this is the operator that you have. Okay, so this is the setting. Again, I keep on. This is my abstract PDE. I keep on changing it slightly all the time, but you understand it from context and the solution operator. So you have to find now a surrogate based on DNNs from the data itself, and you have to deal with functions. There's no way. So we have to do some sort of smarter reduction to finite dimensions, because computation have to be anyway done in finite dimensions, but we have to do something smart, some sort of a smarter reduction. How do we do that? So, okay, so here's the solution. Okay, that the cheating was to have a finite dimensional problem. Now we don't have a finite dimensional problem. We have an infinite dimensional problem. And let me try to explain this, because this is going to be rather germane to what we are discussing. So let me try to explain this relatively well. So what are we seeing here? So we are seeing a fluid flow. So this is the Navier-Stokes equation, incompressible Navier-Stokes equation in 2D, because most of our examples are in 2D, things scale to 3D, but of course the computational challenge is formidable. But let's say this is in 2D, and what you're seeing here is a vorticity of the fluid. Okay, vorticity is just the curl of the velocity. We have a velocity field. This is the curl of the velocity. And this is the initial vorticity. Let me call it as omega 0. And this is the vorticity at a certain time as a function of space. Both of them are functions of space, so as a function of space. So you can see that, okay, you start with some vorticity. There are some vortices here, some negative vortices. Vorticity can have either side, right? So some negative vortices here. In 2D, it's a scalar. In 3D, it's a vector. And that makes all the difference for fluid flows. But the point is, then it evolves. And you cannot have predicted, just by looking at the initial vorticity, how the final vorticity is going to look like. It's impossible to predict. There's no formula to write down. You have to. This has been done with some numerical method, some spectral method, or I don't remember what's the numerical method, but some numerical method. So essentially, I have been given an input function, initially a function, and I have been given an output function. And my task is that, can I have a surrogate? Can I learn this function from data? I have some data. Earlier, I used parameters, but now I cannot use parameters anymore. These are genuinely given as functions. Okay, images in this sense, right? So the first solution, which is actually a very trivial and a useful solution, is the following. And let me explain it with some context, otherwise, because this is important. The point is, I have to do computations in finite dimensions. There is no way I can do this in infinite dimensions, so I have to do something in finite dimensions. So I have to do some finite dimensional reduction. Okay, this is how I do my first reduction, which is I use sampling. So I have a function which is an infinite dimensional object, because this can be evaluated at every point. What I do is, okay, I say I cannot, this is numerical analysis, right? I cannot have every single point, because I cannot store every single point on a computer. I take a bunch of these points, a discrete finite set of these points. So in this particular case, just visually, I have taken 16 by 16 points, 16 in this direction, 16 in this direction, just for simplicity. Okay, but in practice, during my training, I'll take 64 in each direction, so because I don't want to show you 64 points. So I take 16 by 16 points, 256 points. In practice, 64 by 64, so 4,096 points. So 128 by 128, which is a much larger number, 16,384. But anyway, this is 16 by 16 points. and I sample the function at these 256 points. So instead of having a function, I now have a vector of vorticity, and each entry is the vorticity at these points. So I have a vector which is 256 dimensional, 4096 dimensional, 16,384 dimensional. So that is roughly the scaling that I'm thinking about, right? So now my function is effectively being reduced at the input level to a vector, a large vector, much larger than the parametric vectors that we had before. So this was the advantage of parameters, right? Because they were representing my function in a much more compressed manner with 20 parameters instead of having 256 even under very coarse grid, and much larger when you take larger grids. I can do the same for my output, right? My output is also a function. I can sample it to 256 points or 4096 points and so on. So essentially, I have, just by taking this one very simple step, I've reduced my infinite dimensional problem, which is mapping a function to a finite dimensional problem, which is mapping a large vector to a large vector, right? So remember that this problem here instead is mapping W0 at xj, j from 1 to capital N, and this is mapping it to W, the omega rather, omega, this is a vector now, right? You can put whatever order, you can take the raster order, like what people do in images. That's not that important. This is at time 1, but at points xj, same points. I could take different points, no one stops me, but let's take for simplicity the same points. Now, as I said, n is the number of points, 256, 4096, 16,384, and so on. It sort of starts scaling in different manner, right? So now, all that I have to do is I have to now go, just by doing this sampling, I've reduced this into a finite dimensional problem, and I can use deep neural network. I can map between them using a deep neural network. Of course, this will be a very, very big network, because if you have 4,000, yes, James.
The sampling, can that also be seen as parameterisation with like this a hat basis or something? So it's where's the exact difference?
It can be seen as a parameterization, except that it is not a fixed parameterization. Because when you change the number of points, the parameterization also changes, right? So this is not we're not reducing everything to one fixed set. We have a set that can grow or contract depending on the number of sample points. Indeed, you can think of it, and we will see that in a second. But you allow these points to change. That's the whole point in some sense, right? That you allow these points to change. But nevertheless, the first challenge is that even if I have 4096 points and 4096 outputs, it becomes harder to sort of put in a deep neural network, because its input dimension is 4096, output dimension is 4096. So my network would be rather big. So already from image processing, computer vision, we know that for images, it does not make any sense to take this fully connected MLPs, multi-layer perceptrons. We should take more structure, and this is where CNNs come in, right? And this is, I think you had a lecture, right? In the very beginning, you had some introductory material, at least on CNNs. And roughly speaking, what they are convolutions, means we are going to see that in later on today. But essentially what you can think of is that, if you remember, the neural network is essentially let's say this is the Lth layer. Let me call it as, okay, VL, let's say, plus some PL, right? So this is the weight matrix, this is the bias vector. So this weight matrix would have been a 4096 by 4096 dimensional matrix if I would have taken the entire structure, a dense matrix. So this would be a sparse matrix, right? So you have a sparse matrix structure, because this is what convolution does. It has a very sparse matrix structure, so it has some there's some non-zero elements. This is just a simplification. And then it has some zero elements. So this is the structure of the matrix. So it has a sparse matrix, and this is what is shown by this little sort of moving window. This moving window is what hits you and gives you non-zero values, and you keep on changing it. So this here is a representation of a CNN. But you could take a MLP if you have the computational resources. You could take MLP. A CNN is a MLP, but with some structure. That's all that you're doing, right? And then, so you have this mapping between 4096 and 4096. Instead of a DNN, you take a CNN, more structure, good. And then you get a 4096 dimensional output. But remember that my target is not something which is sampled. My target is a function, right? So I have this function on 16 by 16 grid, 64 by 64 grid, 128 by 128 grid. So what I can do to get it at every point is to use interpolation, right? Interpolation tells me that if I have a discrete set of values, I can automatically interpolate and get a continuous function, right? So this is a very, very simple way where we do a finite dimensional reduction, and yet we are able to do the processing in the sense that I start with a function, sample it in a grid, use a CNN. This is one particular architecture. I could have used something else. And then I have values on a grid as outputs, and then I go back to the function by using interpolation. Is this scheme clear? It's a very, very straightforward scheme in some sense. And the question, and then of course, our training is done at the level of these grids, right? So the weights and biases of this network, these WLs, they have more structure than what I'm saying, but these are done at the level of this 16 by 16 or 64 by 64 grids. Does it work? The answer is yes, to some extent, because just to give you an example, I took a slightly more difficult problem because this problem is too easy in some sense. We'll talk about that later, but this is the same setting. So I still take perhaps this the velocities instead of the vorticities. So it's still Navier-Stokes with a very high Reynolds number, so that it's essentially approximating inviscid flow, so that interesting things happen. And this is a very well-known problem in fluid mechanics, computational fluid dynamics, which is that you take a shear layer, can happen here in the atmosphere. So you take a shear, so the velocities go like this, and the vorticity is concentrated along this little shear, and then vortices are shed. So this is how the solution evolves. These are the velocity evolves. The velocities, this is just the x velocity for visualization, and this is what happens to it. So I do the training on a 64 square, and then of course what I have is I have a ground truth, right? So this ground truth is generated by a numerical simulation, but I can do this if I want at 16,384 squared. I have the code and the compute to do it, but it is done at 1,024 squared. Okay, 1,024 squared is fine enough resolution. So I have a ground truth, and because I have this function, and this is a question that James asked, I have the freedom because it's a function, right? It's not a vector. So I can evaluate it at 16 squared, 32 squared, 64 squared, 128 squared, 256 squared, whatever resolution that you want. So I train it at 64 squared. I compare it to the ground truth at 64 squared. And then let's say that this is your training error or generalized or test error. Let's call it as the training error, okay? And the number that I get is 5%. This is neither here nor there. It's some number, okay, 5%. It's satisfactory. It does a good job. So you say, oh, okay, good, that I've really solved the problem in some sense. But this is precisely the issue that I haven't solved the problem. And why haven't I solved the problem? Because remember that I can evaluate this function at 128 squared or at 96 squared. So, and I can also, so I train at 64 squared. It's very important, so pay attention. I train at 64 squared. My weights and biases, everything is trained at 64 squared. But my evaluation can be at different resolutions. It can be at 96 squared, it can be at 32 squared, because it's a function. It's not a particular fixed vector. My parameterization can change. This is the point that I was trying to make. And then, of course, I evaluate and I look at the errors, I compare the errors. And then you see, as soon as I change my training resolution, for instance, if I go to 96 squared, then I get an error which is 3 times more. And if I go to 32 squared, which is a smaller training resolution, smaller than the training resolution, the error is increased by a factor of 5. So in other words, I have not generalized at all. I have not learned a function at all. I've just learned one particular realization of the function on a grid. So this is not operator learning. This is just, in some sense, cheating. I'm still learning a fixed parameterization, a large parameterization, but a fixed parameterization, because as soon as I change my parameterization, it does not generalize. And here the parameterization is in terms of the sampling points, right? Because as you said, this is a parameterization. And this is not my discovery or anything. This has been known for a while, that you cannot just learn functions by sampling them on grids, because you lose a lot of information doing that. So there is an issue there, because what you need to learn is the underlying operator and not just one discrete representation. So this tells you that there is a little subtlety here, that you have to learn some equivalence between the continuous and the discrete, because a function is a continuous quantity. It's in a continuum, whereas vectors, sample points of the functions, these are discrete quantities, and there has to be some connection between them. Otherwise, you don't learn the function. This is a very, very important point. Are there some questions about this particular point that I made? So this graph is what is somehow absolutely crucial. It's very, very important, because it tells you that, as I said, everything is about generalization. So no generalization is happening. In other words, if you remember, coming back to the airfoil example, even though we had the possibility of evaluating on 30 basis functions, the answers will be very bad, because you are simply not generalizing. You're learning only on 20 basis functions. So that's why I keep on, I took my time to explain this, because it's very pertinent to what I'm going to say. Questions? No? Anyone on Zoom who wants to ask a question about this? Okay, so this is the key point, right? So we have not learned the function. We have just learned one particular realization of it. And this is really a challenge from various angles. And let me try to explain that. So remember that at the end of the day, my operator, my mapping, so this is for Darcy, right? So this was the elliptic case, Darcy. So my operator is a mapping between the input and the output, right? These are functions, these are functions. But in practice, of course, I have to work with discrete. There's no choice. I cannot even, unless until I use some symbolic package, I cannot even write a function on a computer. I have to approximate it with something discrete. But the problem is that there are multiple ways of doing it discrete. You could change the resolution of the grid. You can have you can have the same grid, or you could change the resolution as we did in this particular example. Or what can be even more frustrating is that your input can be on some random points, point clouds as these are called, outputs can be on point clouds and so on. So there are multiple discrete representations of the same function. The same function you can approximate at 16 squared, 32 squared, 64 squared, or you can approximate it with fixed sort of uniform points. You can approximate it with random points, quasi-random points, and so on. All of these are bona fide representations of the function. But at the same time, they have the same underlying reality. But to us, when you look at them discretely, they look very different, even though they're representing the same reality, right? And this is where you need to understand this concept of some equivalence between the continuous and the discrete. You have to go between the continuous and the discrete in order to be able to solve this problem. Okay, so what I'll do in the next 15 minutes is really try to attack this particular question. How do you link the continuous and the discrete so that you can design architectures, frameworks, which go seamlessly between the two? And this is mathematical. It's not mathematically that difficult, but it's a little subtle. So you have to pay a bit of attention. Okay, so let us try to continuous discrete or discrete continuous equivalence, whatever you call it. I should have switched. Now I made a mistake here. So essentially, what is the problem here? The problem here, let me try to explain, is that this is my, let's use some pen here. So this is your continuous world, this one here, right? So these are function spaces. So this is this guy here. These are function spaces. Right? And your actual operator, your ground truth, is sitting right here. But because of the way in which our digital computers operate, that will probably change when you have analog computers, but at least for digital computers, we have no choice but to work with the discrete. So this, for instance, could be a grid. Values on a grid, of course. This is values on a grid. Let me use another pen. And this is your discrete operator. Right? So this is your discrete operator. So what is important is that there should be ways of going between one and the other. So this, for instance, was sampling. I showed you sampling. Here I showed you interpolation, sampling, and interpolation, such that this happens seamlessly. That when you operate in the continuous, or when you operate in the discrete, rather, it's the same as operating in the continuous, because that would solve the problem, right? So how do we do this? I mean, this is sort of the crux of the argument. And let me just continue this. And the framework is very recent, but it sort of is not hard to understand. So what's going on is the following. So at the end of the day, to go between the two, you need two elements. Okay, so let me give them some names. I call them as an encoding. E. So this is a mapping between your function space and your discrete space. So this guy here, right? This is a mapping between the function space and the discrete space. This could be sampling on a grid, for instance. And then you have a decoding, or I prefer to use the word reconstruction, because it's really not between vectors of different sizes, but between vectors and functions. Otherwise, it would have been. So reconstruction. So I called it as R, which is a mapping the other way around. It goes from the discrete to the continuous. So this guy, okay? And the same plays here. Maybe they are different, but just for simplicity, I took the same, okay? So now the point is that the continuous and the discrete can be related to each other in a particular manner. So if you think of it, now focus, that this was a mapping between X and Y. One way to realize this mapping is I go from X to this X, or calligraphic X to X. That's from the continuous to discrete with E. So I do this. Then I do my work here, G, and then I go back again by using this guy here, R, right? So this exactly what we did before, that we could have, where was the picture here? That first we went from the, let's say from the continuous to the discrete by using the sampling. So this was my E. Then I did some processing there. This was the CNN. This was my operator G, discrete operator G. And then I went back up with the interpolation. Okay, so this is the algebraic structure. This is the scheme somehow in how I operate. Okay, so now what we want is that these two things should be exactly the same. This is what we want, because then working with the discrete is the same as working with the continuous. I do all my work at the discrete, but then there is something which is going on at the level of the continuous, right? Unfortunately, that is not always the case, because if that were the case, then I would not have gotten this picture here, right? Because then it would have always corresponded to the same continuous function, but it didn't. So the error in doing this, there's a name for this error. Means some of you who have done some signal processing in electrical engineering probably know this error. So this error is called what is called aliasing. Okay, aliasing error is when the equivalence between the continuous and discrete. So now this is the way, if this would have been true, then there would be some equivalence between the continuous and the discrete. But that fails, then you end up with some error. It's an operator because it acts on functions. And this is what is called the aliasing error operator, which is precisely the gap between them. So this is the mismatch, okay? The mismatch between the continuous and the discrete. I'll give you some concrete examples in a minute, but this is the abstract level. And all that we asked is that this should be made zero, right? So this, so the operators, let's say the neural networks, these are called, there's a name for them. These are called representation equivalent or resolution equivalent, but I prefer the word representation equivalent neural operators, or ReNOs. All that they do is that these by construction are such that this error is equal to zero. So they don't alias at all, okay? So you want to construct them, they're not available there. You have to construct them in such a manner that there is no alias, that whether you work with the continuous or whether you work with the discrete, you get the same answer, okay? Of course, you can say that maybe in some problems, it is impossible to have an exact realization of this, but at least they should be small. These aliasing errors should be small, hopefully vanishingly small, right? But now remember that neural networks or neural operators, as we are going to call them, these are compositions, right? So I missed something here. So these are typically compositions. They are done layer-wise. So what we demand is that, I don't even know why I wrote this, but this is equal to 0. Is identically equal to 0. So we want that this, this was a bit. So you want that for each layer, whatever layer that you're in, this aliasing error should be 0. But once you have a composition, then 0 composed with 0 is 0, composed with 0 is 0. So if every layer of your neural network or neural operator, as we are going to call it, satisfies this property that there is no aliasing, then the whole operator does not have any aliasing. So that is the construction. And what is the advantage of this construction? And as I said, these objects need to be constructed. They have not yet been there. They need to be constructed. But if you are able to construct them, then an immediate corollary of this construction is the following. That if you have different grids, for instance, remember that these G's here, these are mostly different. This G here is on a grid, right? So this, you can think of it as on a grid. So you have different grids. So one grid would be called as G, and the other grid would be called as G prime, for instance. Then what happens is that there is a natural connection between them. What is the meaning of this natural connection? The meaning of this natural connection is that, remember that your underlying operator is capital G, and you're going to approximate with this G. Similarly, your underlying operator is capital G, the same operator, that does not change. What changes is your grid resolution, for instance. So you have a new grid resolution G prime, but you have the corresponding R prime, E prime, and so on. And these two things, they are sort of related to each other because you can go from one to the other. You can go from G to G prime. And the way you go from G is you start with G, go back to your function space. So this is what you do. So you go back to your function space. Then you work with the continuous operator, which works here, and then go to the discrete again by using this R prime here. So this is the construction that is there. And this links G and G prime, the operator different grids, because all that it says is that, okay, I first went from this grid to the continuous through this operator, and then composed again to, so in other words, so we start with, let's say, let me take a minute to explain this because this is important. So I start with this grid, let's say 64 by 64, just for concreteness. Then I go up to the continuous by using this R, this reconstruction operator. So I started here. So I go up to this here, or rather, I started here rather, and go here to the continuous. And then I go back to the 128 by 128 grid through this. So there is a natural connection between them. And the same at the output side, right? And when you combine them, this is what you would get. If this was not 0, if there was an error here, then it would automatically show up. Because we used to derive this expression, it's very, very straightforward, that I use the fact that the aliasing error between these two grids is equal to 0. In other words, you start with one discrete, go to the continuous, then come back to the other discrete. And when you combine them, because these diagrams, these are called commutative diagrams, they commute, you can easily transfer them. It's rather straightforward. And if you did not have this, if this was not 0 and this was not 0, there would be discrepancies. Because once you go from the discrete to the continuous, you make an error. And then when you come back from the continuous to the discrete, you make another error. These errors can sort of couple with each other and give you large errors. Of course, they could also, if you're lucky, cancel out. And this also sometimes happens. But mostly, by design, you shouldn't have this. You go from, so if you have two different grids, you start with the coarse grid, let's say coarse and fine. It could be fine and coarse also, but you start with the coarse grid, you do the calculations, the calculations are done there, but there is a continuous analog. So essentially what is happening at the discrete is mirrored at the continuous level. You do that, and then you come back to the final grid. So there is a natural way in which this transfer happens. And I'll give you a concrete example. So if you had this representation equivalent neural operators, which allows for a seamless match between the grids, then you are able to do this. Let me give you an example, and then perhaps it becomes clearer. Because what I haven't given you is what is the function space, what is the encoding, what is the reconstruction, and so on, because there are, of course, multiple examples of it. But the example that we are going to concentrate on quite a lot, just for simplicity in 1D, but this can be done in any dimensions, is by using what are called band-limited functions. Okay, so if you just use arbitrary square integrable functions, you cannot do this because there's no way you can marry the continuous and discrete. But if you take band-limited functions, what are band-limited functions? So simply think of it, if you had a Fourier series, for instance, so you had u of x is given by u hat k, e of I kx, something like this. So that's a Fourier series. All that you do is that you work with a finitely many Fourier modes. Okay, so that is band limited. So you only have finitely many bands. And these are very, very important class of functions because, of course, the bands can be large. If you take 1,000 frequencies, you can represent quite a lot. But the bands are not infinite, right? So this is the important point. So in that case, if you have band limited functions, then the encoding here between the band limited functions is given in terms of pointwise evaluations. So you can just take a function, sample it on a grid, and then you can go back by using an interpolation using what is called a sinc basis. So all of you, I hope know what the sinc function is. So, sorry. So sinc, where is it? Sinc of x is roughly sine of x, roughly. There are some constants, sine of x by x. Okay, this is a very well-defined function, very common in signal processing. And the point is that you can, so these VJs are my, so the continuous is the function, the discrete is given by point values. And once I have the point values of a function, then all that I do is I can use the sinc to go back to the function. Okay, so in this case, there is a nice match between the continuous and discrete. And if you have a dense enough grid, so this is what is given by the Nyquist barrier. So if the number of grid points are double that of the frequencies that you are keeping, then there's a bijection. Means the continuous and the discrete are identical. So whether you have a function or whether you have its point values on a dense grid, they are one and the same. And the link between them is given by this particular thing. So if you have this setting, which is a setting that we are going to use quite a lot, a Cartesian grid equispaced with enough points to resolve the functions that you are approximating, then whether you are working with the continuous or the discrete, the answer is identical. Okay, and this is the Nyquist-Shannon sort of theorem, some people call it. This is very common in signal processing. And you can look up Wikipedia to see that what does it imply. It simply implies that if you have enough frequencies, if your function has a certain number of frequencies, and if you sample it at enough equispaced points, you can exactly reconstruct the function. Okay, so this is the setting that we are going to utilize. And let me very quickly tell you that based on this setting, it's a very concrete setting, we can already prove or show very simply that convolutions, CNNs or MLPs for that matter, these are not representation equivalent. Because what are convolutions? Convolutions are first you do convolution, activation, convolution, activation, convolution, activation, right? So if you start with a discrete convolution, so these are discrete convolutions. So essentially I have a function C. Now, I keep on changing notation. I have a function C and I have some convolution kernel K. And the action of the kernel is I have a fixed window, right? So I have a fixed window as I showed you, and I multiply the kernel functions, shifting the underlying functions. So in other words, the way it happens is that I have a signal, let me call it as C here. And then I take a convolution kernel. This is my convolution kernel, which I give here. And then at every step, at every iteration of this kernel, I hit a certain number of values. At the next iteration, I'm going to hit these values. At the next iteration, I'm going to hit these values. Sorry. At the next iteration, I'm going to hit these values and so on. That's what convolution does, right? You run through, you slide a window through the signal. Now, why is it not a ReNO in this particular case? The simplest argument is, if you take a finer grid, it could also be a coarser grid. If you take a finer grid, so this is the finer grid, as you can see here, I have the same kernel. I'm using the same kernel because the kernel is exactly the same, whether I'm not resizing the kernel. Then let's do so I take these three values. Remember that the orange here had three very different values. These values that you're multiplying are exactly the same, right? This is exactly the same values, but these three are very different from these three. And of course, they are not identical. And then when you slide the window, so for the next one, which was in red, I take these 3 points. Again, they don't match the 3 points in the red here. And then for the green, I take these 3 points. Again, they don't match the 3 points on the green here. So you start making, so the multipliers are exactly the same, but the point, they are close to each other because of course it's a signal on the grid, but they are not identical because the kernel is not going to change. It's exactly the same kernel. So algebraically, you see that they cannot be resolution dependent because the values on different grids are exactly completely different from each other. So because of that, you cannot get this answer here. They are not identical to each other. Because of that, it is not the convolution is such that it cannot be a ReNO. It cannot be representation equivalent. And this sort of justifies what is happening here, right? So if you remember, I started out with this picture. So on a fixed grid, you got whatever results. But as soon as you change grids, you resized your kernel. You did not resize your kernel, but you are multiplying the inputs and the outputs with different values. So of course, you got different results. And these errors group. Because of course, each time I slide the window, I make a small error. but there are like 5 layers. So of course, these errors accumulated. They might be small in the beginning, but they could accumulate exponentially in the number of layers. Because of that, you got 5 times the error, even though you just resized the grid a little bit, right? So this was sort of the effect of not having this property, of having aliasing errors. So what's the solution then? So we have to design architectures, we have to explore architectures that reduce this error or best eliminate them, right? So that would be the objective. Already in the tutorial, you saw one such architecture which might have that potential. And this is what we are going to do, but only after how many days? Now we have a break next week, right? So after in 2 weeks, right? So in 2 weeks, so now you can rest for the remaining 2 weeks. So finish your assignment. Good. Okay. See you in 2 weeks.